Welcome back to another episode of Introductory Organic Chemistry. Today we're going to talk about 1,2 shifts of activated amides. But before we get into that, let's go through the practice problems that I assigned last lecture. Now in this first problem, we start with 1,3,5-trimethoxybenzene, and we have to propose a synthesis of the following product over several steps. And the rules are that we can only use common reactions that we've talked about so far in the course, as well as very common reagents, and you'll see what I mean when we go through the solution. So in this first reaction, I would do a Vilsmeier to install a carbonyl. Once this carbonyl has been installed, we can then do an aldol condensation with acetone. Both DMF and acetone are common reagents, which is kind of what I was getting at, but I didn't want to spell it out too much, so that we can make this alpha-beta unsaturated ketone product. Now you might be wondering why acetone doesn't react with itself. It could, but aldehydes tend to be much more electrophilic than ketones, if you recall from the earlier lecture on aldol condensations, which I'll put a card to here. Now, we want to do something to get that alkene that we had in our product on the previous page. And so what we could do is we could prepare a Wittig reagent. So isopropanol is a common enough reagent. We'll treat that with thionyl chloride to get the corresponding chloride. If you wanted to start with the chloride, this would be okay, but in case you thought that that was too obscure, we'll just take this alcohol, treat it with thionyl chloride, get our 2-chloropropane. Once this is treated with triphenylphosphine, we'll have our Wittig reagent, which just needs to be deprotonated before it can do its olefination. Now, first things first, before we can install that new alkene using the Wittig reagent, we have to first do our cyclopropanation. So we're going to use the Korey-Chekhovsky reaction that we talked about in the last video, and that should just react in a 1,4 addition as we have an alpha-beta unsaturated ketone, giving us this cyclopropane. Now that this cyclopropane has been installed, we can do the Wittig as our final step. Deprotonation will occur using N-butyllithium, giving us this tetrasubstituted alkene as our product. Now, in practice, this reaction might actually be kind of challenging because that's a tetrasubstituted center, but there's other olefination conditions that exist, such as Julia olefination, that we'll talk about in a future video. In the next problem, I wanted you to fill in the blanks. And so initially we start with this acetyl chloride derivative, which will react with this. And so first what we get is we get this 2-chloroacetophenone product. We only get paraselectivity as this is a bulky group, and in general, electron donating groups tend to prefer paraselectivity. Now, once we treat this with this isopropyl mercaptan, we're going to just undergo an SN2 reaction, displacing the chloride. This is an alpha chloroketone, so this is a really good leaving group. Next, what we're going to do is we're going to do an epoxidation reaction, another Korey-Chekhovsky, which is just going to give us this epoxide in this case, as we don't have any Michael acceptors present. Finally, we're going to undergo a nucleophilic attack at the less sterically hindered site with methyl magnesium bromide, giving us this tertiary alcohol product. Hopefully this was relatively easy to follow. Now in this final problem, we have a paper from Carrera and co-workers where they use the Trost ylid that we talked about in the last episode. Now if you're not familiar with the Trost ylid, I'd encourage you to check out the last episode, which I'll include a card to here. So initially what we're going to do is we're just going to make an epoxide, but the epoxide that we get is this really strained, interesting looking 4,3,3 tricyclic system. And to open this and rearrange it, all we have to do is treat this with lithium iodide, a very weak Lewis acid. So what we're going to get is this 4,4 bicyclic system, which can then undergo a Wittig reaction. Now, what they do in this paper is they take this really clever Wittig reagent, which gives vinyl ether as a product. Now, if you treat this vinyl ether with an acid, this is actually just a masked aldehyde. So this is a cool way to essentially have a nucleophilic aldehyde equivalent. So this is what they do. So once they treat it with HCl, that just protonates the beta position, making the alpha position a carbocation, which can be attacked by chloride, and undergo hydrolysis, affording the aldehyde. Next, they do a Pinnick oxidation, which is just a conversion of an aldehyde to a carboxylic acid. If you're not familiar with this oxidation, I'll include a card to the video about that here. And essentially, once this carboxylic acid forms, because this is a really strained system, this can easily protonate that amine and then undergo nucleophilic ring opening and form this lactone cyclobutane as a product. And so we've just opened up the azetidine, and an azetidine is just a 4-membered ring with a nitrogen in it. So hopefully this was a useful synthesis that covered many of the topics that we've already discussed in this course so far. Now let's get to today's material, the 1,2 shifts of activated amides. So the general reaction is you take a carboxylic acid, which could also be an amide, just depending on conditions, prep the amide, and then undergo a rearrangement reaction, which essentially just deletes the CO and puts a nitrogen in its place. Now, if we do these reactions thermally, This doesn't occur via a nitrene, although photochemical conditions can go via nitrines for acyl azides, for instance. This just forms an isocyanate as an intermediate, which if you do this in water, it'll form an isocyanic acid, which can just decarboxylate to give the amine. So there's three main reactions that are named reactions that fall under this set of reaction conditions. And so the first one would be the Hofmann rearrangement, which was discovered in 1881. The next would be the Curtius rearrangement, discovered in 1885. And finally, the Lossen rearrangement, discovered in 1872. These three references here are the original paper where they were first reported. Now let's look at the Hofmann rearrangement. So initially, if you take an amide, which could be easily prepared from a carboxylic acid, and you treat this with bromine under basic conditions, you'll form an N-bromo species, which can be deprotonated. This bromine makes the NH more acidic, and then the R group is able to attack and move over. But to make this a little bit clearer why the R group with electron density attacks a negatively charged nitrogen, I prefer to explain this mechanism by drawing this as the nitrogen version of an enolate. So if we have the negative charge there, we can see that the negative charge collapses down. That gives this R group an excess of electrons, which is able to attack over onto the nitrogen and displace bromide as a leaving group. I find this rationale to be a much better explanation than most of the mechanisms shown online and in textbooks. And this is more intuitive to me than a negative charge attacking a negatively charged nitrogen. Okay, then we get our isocyanate, which can then react with water to form this isocyanic acid, which could just decarboxylate, the same way that carbonic acid just decarboxylates in water, giving us the amine in this case. So some examples of the Hofmann rearrangement include the treatment of this heterocycle, where we undergo just a simple decarbonylation, giving us this NH2 in the presence of a dimethyl acetal. Another example includes this N-tosyl containing piperidine, which is able to easily undergo decarbonylation in good yield. Now the next reaction we'll talk about is the Curtius rearrangement. So typically the way that this is done is you treat an acyl halide with sodium azide. Once you have an acyl azide, we can draw it in several different resonance forms. Now in this case we don't need a base necessarily because you can see that there's no NH we need to deprotonate, but we could draw a resonance structure like this where we again have this enolate-like system which can then undergo collapse of electrons back down, which gives the R group an excess of electrons which can attack the nitrogen, displacing N2 as a leaving group, giving us again our isocyanate. Following the same process as before, we're afforded with an amine. So a couple cool examples of this include the treatment of this quinoline tricyclic system with base in the presence of water and HCl. This is then able to undergo decarbonylation and elimination of nitrogen, giving us this primary amine product. Now, one of my favorite examples of the Curtius rearrangement is this reaction from the Schoenbeck lab out of Germany, where they treat this NCF3 carbamoyl fluoride with sodium azide to get an acyl azide. This acyl azide is then able to undergo Curtius rearrangement to form an N-trifluoromethylhydrazine. So not only can you form amines from amides or from acyl azides, you can also form hydrazines this way. So this is a useful N-N forming reaction. N-N bonds are typically challenging to prepare without using something like nitrous acid, for instance. So this is a really cool reaction that's worth noting. It's also neat to see a nice stable NCF3, as those tend to be somewhat unstable compounds. So the last and final reaction is the Lossen rearrangement. And so the way that this works is you have an N-hydroxyamide. These can eliminate on their own. However, it can help the reaction if you use an activator, such as acetic anhydride. So once this forms an N-acylated species, it's easier to deprotonate this, and again, we get this resonance structure where we have an enolate-like system. This is then able to collapse down, give the R group an excess of electrons, which can attack the nitrogen, and displace this carboxylate as a leaving group. This is a 1-2 shift, and the reason it's a 1-2 shift is it moved from the carbon to the nitrogen, which is one atom over, 1-2, 1-2 shift. So I haven't really highlighted that in all these cases, but this is a type of 1-2 shift. Okay, so now we get our isocyanate, and the same hydrolysis procedure can occur. So a couple examples of this include the treatment of this really interesting cyclobutane-containing purine derivative with CDI. CDI is an activator, so essentially what this does is it gives you an O-carbonyl imidazole, which is still a good leaving group. It's just instead of an acetate or something as a leaving group, this can just collapse to imidazole and CO2 ultimately. This is a nice reagent that's convenient to handle, and it can be a good alternative to phosgene, which is extremely toxic. So CDI is a nice other way to dehydrate and couple reagents, but in this case, they're using it to activate the OH. So once they do that, they undergo the Lossen rearrangement and they just treat it with acid to get this protonated product, which they were able to purify. In this next case, they use acetic anhydride as a catalytic activator. For some reason, under these conditions, they only required a catalytic amount of acetic anhydride. I'm not entirely sure why it doesn't react with the DMSO. Perhaps it does. It could just be that these are lower temperatures, so the DMSO doesn't react. But if you recall from the Swern oxidation and related reactions, acetic anhydride can be used as a DMSO activator, and I'll include a card to that here. Now in this case and the upper case, we can see that both of these are aliphatic amines, but the majority of the literature on Lossen rearrangements involve aniline derivatives as products. So I'll give you a couple practice problems for this lecture. These will be 2 multi-step synthesis problems, and at one stage or another, you're going to need to demonstrate how you could make an amine using one of these activated amide rearrangement reactions. So this is the first problem. Just fill in the blanks and identify the type of reaction occurring at each stage. Now in this next problem, I just want you to fill in the blanks. This might be a little bit more challenging. I decided to omit conditions here, and in the remaining cases, you just have to figure out what product would be formed under the reaction conditions given. And so I hope that this has been a useful lecture on 1-2 shifts of activated amides, and I would appreciate it if you left a like and subscribed, and I hope you have a great day.